All right, it's a pleasure to introduce our second speaker this morning. It's Enric Ventura from UPC Barcelona, and he is going to tell us something about the central tree property and some average case complexity results for algorithmic problems in free groups. Enric, please.
Thank you. Thanks for inviting me to give a talk in New York. It's online, but it's always nice. Okay, so we'll try to talk about a recent result. This joint work with Malika Roy and Pascal Veil, and it's a recent paper on average case complexity of some improvements of classical algorithms, improved from this average case complexity point of view. No? I will first talk a little bit about classical Whitehead's algorithm, and then some improvement that we are doing with using this central tree property. Okay. Well, general setup for algorithms. A decision problem is a problem where the set of inputs is well defined, and it is well defined which property are you checking. So the answer of the algorithm should be yes or no, and the set of inputs in a given problem usually comes with a notion of size, or also called length, which is a natural number assigned to every input, but in measuring the size of the complexity of the input, but in such a way that for every natural number there are finally many inputs of a given size. Yeah, and then solving a decision problem is just finding an algorithm in the sense of a Turing machine. There are other models of computations, but let's restrict ourselves to Turing machines. If there is an algorithm answering correctly for every input. Okay, and the notion of complexity, worst case or average case, is what everybody knows. No? The time taken by an algorithm over a particular input is the number of steps, the number of elementary steps, whatever you count them, taken by the algorithm to give the correct answer on U. The worst case complexity is the function from naturals to naturals, measuring which is the most expensive input among all the inputs of a given size. And then the average case complexity is the same function, but instead of taking the maximum, you average over all inputs of a given size up to n. Yeah. Of course, all these functions are measuring the how good or how bad is our algorithm, but they are only interesting up to asymptotic equivalence. No, the exact values of the functions are not relevant, but only the whether they are linear or quadratic or logarithmic, whatever. Of course, the average case is less than or equal to the worst case, but as we will see in a minute, there are significant cases where the average case complexity is much smaller. It's asymptotically smaller than the worst case complexity. Meaning that maybe our problem has instances that are very hard compared with most of the instances that are much easier to be solved. Okay, and a very naive, very easy idea to try to improve the average case complexity of, suppose you have your favorite algorithm. If you find a variant of the algorithm running faster, then you are improving your algorithm. But if you find this variation running fast, but only on a certain subset of the inputs, this may be enough to improve the average case complexity as soon as the set of good inputs is big enough. Yeah, you can do this very easy variation. Consider a new algorithm which, given an input, checks whether the input belongs to the nice subset, and in this case you run the fast algorithm, and if not, you run the small one. You run the slow one. This is going to be, in the worst case, it is going to be the same thing because the bad inputs are here, But if the subset is big enough, most of the inputs are going to fall into the fast algorithm, and then this improves, while leaves the worst case complexity untouched, it improves a lot. It could improve significantly the average case complexity. Okay, and this was the idea recently exploited by Vladimir Spielrein in this paper about an improvement of the Whitehead of one of the Whitehead classical problems. Okay, so let me talk a little bit about the classical Whitehead algorithm for deciding whether a given element is primitive. So let's concentrate just in the free group of rank R. R is fixed. And then Whitehead, almost 100 years ago, proved that you can solve algorithmically the following problem. You are given an element in the free group, always as a reduced word or reduced cyclic word, if you prefer. And then you should decide whether the element is primitive in the free group or not. And the classical Whitehead algorithm works in this, in time quadratic with respect to the length of the input. And I make it a little bit more precise. I say quadratic times 4 to the R times R, where R is the rank of the ambient group. This is not relevant here because the rank is a constant. So this 4 to the R is nothing. Is just a constant, but in the way that I will apply in 10 minutes, this dependency will be important. How does this classical algorithm work? Well, a very easy observation: an element is primitive even only if the shortest possible element in its orbit has length 1. So it's even only if you can map it by an automorphism to a single letter. And then Whitehead introduced this so-called Whitehead automorphisms, which are very easy ones, just fixing one letter and sending the other letters to themselves, pre and post multiplied by the fixed letter, maybe to the 1 or to the -1. Yeah, there are that many Whitehead automorphisms, and the key point is that he managed, as part of this peak reduction lemma, he managed to prove that even if the length of a word can be decreased by some automorphism, then it can also be decreased by some Whitehead automorphism. Since there are finally many Whitehead automorphisms, just check them all. If you can decrease, replace your word by the shortest one and repeat again. And if you cannot decrease anymore, either you are at length 1 and so the original element was primitive, or if you are at the bottom of the orbit and the length is bigger than 1, then W was not primitive. Yeah? This is essentially quadratic time because the length of the word decreases in the worst case, decreases 1 by 1, and at every step you have linear amount of work to do. Everything, of course, multiplied by the number of Whitehead automorphisms, which are a constant, but exponential, but a constant on the ambient rank. Okay. Whitehead also proved this classical Whitehead scat vertex lemma, which is a nice tool. He defined his Whitehead graph on the word. I suppose that everybody knows these definitions. It's a graph whose vertex set is the set of positive and negative letters, and you put an H between each one of the letters in your word, connecting with the negative of the consecutive letter. Everything modulo n, so from the last letter to the negative of the first one as well. That's why you should assume that your word is cyclically reduced. And then the result is that if the word is primitive, then the Whitehead graph is either disconnected or has a cut vertex, a vertex whose deletion increases the number of connected components. Well, there are several variations and several modern proofs of the original proof was topological, but there are modern proofs by Weidmann and Heusener, and another one by Henry Wilton. Okay, let me talk about two specific improvements of these classical results. Together with my co-authors Pascal Bale and Abdor Roch in 2007, we did the following improvement, looking carefully at the Whitehead graph of your word. You can construct directly the Whitehead graph, decreasing the length of the word as much as possible. So let's say the best Whitehead graph for this particular word. And you can do this in polynomial time with respect to the length of the word and with respect to the ambient rank. Yeah? Remember that this dependency was exponential on the ambient rank. So here, playing with the classical Max-Flow min-cut algorithm on the Whitehead graph, we can cook the best possible Whitehead automorphism for our word in polynomial time, really in terms of n and r. Okay, and then this improves the classical Whitehead algorithm. Just instead of checking all the Whitehead autos, just construct the best one and apply it. If you go down to length 1, then you were primitive, and if not, you are not primitive. Yeah. Okay, this in our 2007 paper, we did the counting, and the worst case complexity goes down to cubic on the ambient rank and quadratic on the length of the word. Okay, this is not an improvement if you consider the ambient rank fixed. It's just quadratic on n, and r is a constant. But in few minutes, I will apply this to a relative situation where the rank of the ambient it makes a big difference. No? Okay. Next improvement on this Whitehead algorithm. It was Spielrein's idea to check this primitivity in a fast way from the point of view of the average case complexity. Given a word, keep constructing the Whitehead graph, but don't wait until the end of processing the full word. Just keep constructing the Whitehead graph H by H, and if at some stage in the middle you realize that the graph is not connected and has no cut vertex, then you don't need to finish computing the graph, because adding new edges will still be connected and will still have no cut vertex. So you can just cut the process at that point and answer no, the element was not primitive. Yeah? And if you arrive at the end and still there is a cut vertex, then apply the classical Whitehead algorithm to check whether W is primitive or not. Yeah? With this improvement, the average case complexity is surprisingly going down to constant. Yeah, this could be a bit surprising at the beginning, but it's because when n tends to infinite, when n grows, a fixed initial segment of W is enough to make sure to say with probability tending to 1, the portion of the Whitehead graph is going to be, say, complete. Yeah, the rank is fixed, the ambient rank is fixed, so a fixed initial segment of W is enough to have a complete graph with big probability. So this more clever algorithm is going to stop with probability tending to 1 in many cases, and very few cases will require the construction of the full graph and the application of the classical algorithm. Okay, in our paper we need to analyze this constant here. How does it depend on the ambient rank? And we do a more detailed analysis of Spielrein's algorithm and prove that this constant is in fact of the order of r to the 6. R is the ambient rank, which by the moment is considered constant, but so this r to the 6 is the same as a constant, but it is of order 6 with respect to the ambient rank. I will use this in a second. Okay, and in the last part of the talk, let me explain this central tree property and how to make how to solve the same problem, but in a relative situation. The relative primitivity problem is the following. Instead of given an element and deciding whether it is primitive in the ambient group, I give you an element and a tuple of elements, and I ask whether W0, first, whether it belongs to the subgroup generated by the tuple, let's say H, and then whether W0 is primitive in H, not in the ambient group. Yeah, this is a different question. Of course, the subgroup is free as well, so at the end is the same kind of problem, but I am asking whether W0 is primitive in the subgroup generated by whatever elements are given in the input. Of course, to analyze this, first we have to check the standard uniform membership problem. Given we have to first decide whether W0 belongs to the subgroup generated by the W's, and in case it does, rewrite W in terms of some basis that you could compute for the subgroup. Okay, here we will consider two possibilities. K, the length of the tuple that you are given from an input, you can consider that this is constant, or you can allow this tuple to grow in length. So K, we can allow K to grow at the same time as the maximal length of the WIs grow. Yeah? If you prefix a function and you allow the length of the WIs and the length of the tuple to grow at the same time with K bounded by some function of the maximal length. It is just a technical detail. Okay, and okay, how to solve this membership problem? This is again very classical thing. It can be nicely solved, for example, by Stalin's graphs. No? By using Stalin's graphs, you construct the Stalin's graph of the subgroup generated by the W's and try to read your element W0 as the label of a closed path at the base point. If you can do it, then you belong to H, and if not, you don't. And at the same time, if you are the label of a closed path at the base point, you can choose a maximal tree from the Stalin's graph, construct the corresponding bases whose elements are in bijection with the H's outside the maximal tree, and then the path spelling your W0. If you keep track this path, you can look at the visits of this path to the H's outside the maximal tree, and this is giving you the expression of W0 with respect to this basis B of the subgroup corresponding to the maximal tree. Okay, if you follow, for example, Twican's algorithm to do all these things, so this is the best. I think is the fastest known algorithm to construct these Stalin's graphs and run these closed paths. All this can be done in time n log star n. Well, here is k as the total number of sum of lengths of the inputs, yeah, which is n is the maximal length and k is the number of words in your tuple. So you can construct the Stalin's graph in time kn log star kn, and then you need linear time to check your W0 to check whether it corresponds to a closed path or not. Okay. All this process can be done much faster from the average case complexity point of view if we use this central tree property that I explained in a moment. It's a property of the given tuple of words. So suppose bold W is a tuple of k tuple of words from the free group. All the time are reduced words and cyclically reduced if you prefer. And we say that the tuple has the D central tree property. D is a parameter. If, well, all the words are long enough, are longer than 2D plus 1, and the property is that the 2D prefixes of length D for your words and the inverses. So write every word as the prefix of length D, the suffix of length D, which is the inverse of the prefix of the inverse of the word, yeah, and then the middle segment, the middle part, which is of length, the length of the word minus 2D. That's why I require all the words longer than 2D for this to make sense. No? Okay, so then the tuple is said to have the central tree property if all these 2D prefixes are pairwise distinct. Yeah? So there is no two such words having exactly the same D prefix from the beginning or from the end. Okay, and a very easy observation is that whenever the tuple of generators has this central tree property, then the Stalin's graph is going to be very, very simple. It's going to consist just on the tree of prefixes. If you take all these 2D prefixes and write the corresponding tree, yeah, so you draw all these prefixes as lines going out from a vertex and do Stalin's foldings. Yeah, you get a tree of prefixes, and the full Stalin's graph will be just this plus the k middle arcs, k connecting arcs of length, spelling the central segments of the words, connecting corresponding leaves of the tree. Yeah? And in particular, the rank of the subgroup is going to be k, and furthermore, the original generators are going to be themselves a free basis for the subgroup. Yeah? When you don't have this central tree property, then more foldings may happen in this central part, and then the topology of the graph could be more complicated. Yeah, but if the 2D prefixes do not coincide, the Stalin's graph is that easy. Okay, and not very difficult counting is telling us that this is going to happen with big probability. Yeah, if you take an arbitrary k tuple of words, the probability that they fail to be to satisfy the central tree property with a given parameter is going to be exponentially tending to 0. Yeah, so if you take an arbitrary random tuple of words, there is probability tending to 1 that this tuple has the central tree property. And in this case, the membership problem can be solved much faster from the average point of view. No? Given a tuple of words, compute the maximal length, construct the tree of prefixes, and check whether your tuple satisfies the central tree property. If not, then which is going to happen with very low probability, run the standard membership problem. Yeah? And if yes, go to step 2, which is essentially doing the same thing, but without having computed the full Stalin's graph. You just have the tree of prefixes, and you have the middle segments. You keep checking pieces of your consecutive segments, of your input, and check whether it can be written it can be read as a closed path at the base point. If not, you are not in W0, and if yes, keep track of the sequences of full arcs crossed crossed by the W0, and this is going to give you the expression of W0 in terms of the free basis of H given by the original generators. Yeah. Okay. Our a little bit tedious calculations give the following average case complexity for this fast membership problem, this fast membership checking. No? When K is considered constant, so suppose that K tuple in the input K is constant, the average case complexity for this algorithm is logarithmic in n, while the worst case was n log star n plus m for the second part of the algorithm. When you allow the length of the tuple to increase polynomially with degree beta, then the average case complexity is beta plus a little bit more. Gamma is any number bigger than 0, while the worst case complexity is beta plus 1 log star n. So here we gain 1 degree, almost 1 degree of 1 polynomial degree difference between the worst and the average case. No? And when the length of the tuple is allowed to grow exponentially fast with respect to the length of the words, then there is almost no difference between the worst case and the average case complexity. This is a general thing that if you allow your tuple to grow faster and faster, then the average case complexity is not going to present a big improvement with respect to the worst case. Okay, and finally, in a couple of minutes, let me combine this with the algorithm to check primitivity and solve the relative primitivity problem in a kind of fast way with respect to this average case complexity. No? Given a tuple given an input, construct the tree of prefixes, check whether the tuple satisfies the central tree property, which is going to happen with big probability. If no, then run the standard membership problem, rewrite W in the standard way in terms of the basis for the subgroup, and then run Whitehead or Spielrein's algorithm to check whether W is primitive in H. Yeah, this is going to be slow, but it will happen with very few probability. And if the tuple satisfies the central tree property, then go to step 2, which is doing as I said before. So you have the tree of prefixes, which is the main part of the relevant part of the Stalin's graph, so plus the k arcs labeled by these middle long prefixes of the wi's. Right? Keep checking whether W0 can be read as a closed path, and anytime you cross you cross fully one of these arcs labeled by these middle segments, you take the new letter with respect to the basis of the subgroup, and at the same time you keep constructing the Whitehead graph of your word. Whitehead graph with respect to with W1 WK, which is now a basis of the subgroup because we are in the central tree property case. No? If you cannot complete as a closed path, then the answer is no. If you can, if at some point you get a connected Whitehead graph having no cut vertex, then you can also stop the process, because even if W0 belongs to the subgroup, it's going to not be primitive. And otherwise, you run the Whitehead or the Spielrein's algorithm to check whether the element is primitive in the subgroup. And doing the calculations, these are the average case complexity of this fast checking for relative primitivity. No? When case constant is logarithmic, when case polynomial is polynomial of the same degree plus a little bit more, plus some epsilon, and when k is allowed to grow exponentially fast with respect to the length of the inputs, the average case complexity is essentially the same thing. It's exponential on the length of the inputs. Okay, and here is crucial. Our analysis before that I did before, this 6 here is because the average case complexity of the Whitehead algorithm was of the Spielrein's algorithm was constant, but a constant being r to the 6, where r was the ambient rank. Now the ambient rank is k, because this primitivity is going to be with respect to the subgroup generated by the W1 WK, which is our subgroup H having rank k. So now the complexity is k to the 6, which makes a big difference. It's not a constant anymore. The real calculations are a bit tedious to follow, so it was not in a talk like this. It's not a good place to make the calculations, but it's just to give the idea of these improvements. Okay, so that's all.
All right. Thank you very much, Enric. Thank you. Okay, so we have a little bit of time for 1 or 2 quick questions if somebody wants to ask. I
have a comment. Can you hear me?
Yes. Yes.
The reason why your algorithm, Enric and Pascal, and my algorithm also, the reason why they work so fast on average is the presence of so-called primitivity blocking subwords, right? So if there's a subword whose Whitehead graph doesn't have a cut vertex, then that's enough to conclude that the element is not primitive. So the question is, are there other automorphic orbit blocking words like that? So in other words, given another element of a free group, not necessarily primitive, apply all possible automorphisms to this element, and are there any subwords that cannot occur as subwords in any automorphic image of the given word? So if one could find any subwords like that other than primitive elements, other than primitivity blocking subwords, that would also allow us to get a low average case complexity, perhaps even constant, for other instances of Whitehead's algorithm.
This primitivity blocking is same as saying you keep computing the Whitehead graph, but don't wait until the end. If at step number 10 you already see that it's connected and has no cut vertex, then stop continuing the computation, because that segment of the word is a primitivity blocking. No? It produces a graph which is connected and has no cut vertex, so any bigger graph will be so.
Yes, and perhaps, like I said, perhaps this could be generalized to other situations, not just to primitive elements. That would be great.
But we for this situation we only know this Whitehead cut vertex lemma is saying exactly this. If we could improve Whitehead's cut vertex to say something else, so if primitive implies something else apart from having cut vertices, then we could have a bigger source of primitivity blocking, no? And same thing for the relative situation, no?
Yeah.
All right. Okay. All right. Thank you very much, Enric. Thank you. Thank you again.
Yeah. Thank you.
Thank you. So
I stop